in. I've been working on similar projects for a longer time, but at some point there was a merge of my other software and Gegl. The way I want to structure this presentation is that I'm first going to talk about what Gegl is and what you can do with Gegl. And then I'm going to introduce another API and kind of show how Gegl is used in different programming languages, both C and Ruby. I'm going to show an XML-based format. And then I'm going to talk about how Gegl works internally. And I'm going to talk about quite a few different things that have not been done that can be done in the future within the confines of the Gegl internals. First, let me start out with talking about what Gegl is. It's a roster processing engine. It's graph-based, has plugins, high dynamic range, supports large images. It's a project started in the year 2000, which was dormant for a while. And on the side on the left there, you have the contributors to the project in order of appearance in the chain block. And the project is actually getting quite healthy. My name was the final name added in June of last year. So all the names below here have come since June 2006. That's kind of impressive in my opinion. It's like those many people around film go, oh, something's happening and want to do something and think this is a good idea to work on. One of the main things that Gegl does is compositing. Compositing is the combination of images to create new images. In applications like GIMP and Photoshop, the one thing you use is having layers. The presentation tool is actually using Gegl, so I'm demonstrating now compositing in Gegl. It's not very advanced. I'm moving the layer around. I can decide I want to tweak the opacity of this layer. Well, that's now just the basics of compositing. Another main thing that Gegl provides is non-destructive editing. Non-destructive editing is a different way of working with images from the way people traditionally, for instance, work in a GIMP. In a GIMP, it's like you decide you want to do something. Yeah, I want to change this image now. I'm going to create a rather nifty effect on it. I'm going to first blur it. So we want to blur it. There we have a blurred image. That's nice. I'll blur it a bit more. Okay. And then I decide that I think I want to threshold this image like that. But since this was a rather dark image, I'm going to actually reduce the threshold I use to see more of the details. But since I blurred my image so much, I don't actually see any details of that chemical factory. So I want to go in and say, well, I want to have this adjustment of the tool. I want to blur it less. And since what I actually have stored is the operations I'm doing to the image buffer, I can go back and change the mind of the parameters of some of the things. And could now add even more stuff and say, I want to take this image and I want to rotate it a bit. Maybe rotate it around the origin. This looks very, very bad, but I want to have it. If I was going to have a proper user interface for this, that should have rotated around the center or something, but the thing works. Yet another thing that's important and one of the shortcomings of the current GIMP core is that the current GIMP core is limited to 8 bits per component. That means when you have a color image, you have red, green, and blue light, which is mixed together to produce the colors that the human visual system can perceive. But GIMP currently only uses 8 bits per component, and that's not a lot. And it's kind of low precision, it's kind of borderline, it's acceptable. We can accept output that is rendered in 8 bits per pixel, but for internal processing, forget about it. You want either 16 bits per pixel, or perhaps you want to go even higher. This image is an OpenEXR image, and it's a 32-bit floating point per component, which is the same thing that Gegl at the moment is working with internally. So I can take that image and say I want to adjust the brightness of it and the contrast. And the first thing we're going to do is to reduce the contrast a bit. And then we should be able to, I want to reduce it even more, because this image has a lot of detail in the sky that we originally couldn't see. That kind of comes forth now, but okay, that's not the way to see the image either. But I just want to show that within the image there is a lot of detail. I don't have proper algorithms within Gegl to do what you call tone mapping, to do what normal people think of HDR, high dynamic range images, as the results you have in these hyperreal colors. But that's actually low dynamic range images. It's a low dynamic range representation of a high dynamic range image. Gegl currently lacks those kinds of transformations. It has some hacky stuff that looks very, very bad, which I threw together over Christmas. But those are kind of some of the basic features. Another kind of important thing is probably that, well, this is not entirely true. Oops. I have moved the file I was thinking to actually show there with another application, so I'll just skip that. I'll rather go forward to the Gegl API. And the core of the Gegl API is that you have a graph. And the example I'm going to look at is this example. And I'm going to actually zoom out a bit more. So we see a rendering of the result. What we see here is that we have loaded an image. That image has been blurred, and over that image we're going to place another loaded image which we have adjusted the opacity. And this end result we're going to display. And the terminology used in Gegl for describing this is that this is a graph, this is a composite signal processing graph. All the circles there, the big ellipses, are nodes. Some of the nodes are source nodes. Both of these are filter nodes. Filter nodes are nodes that have one input pad and one output pad. There is also a composer node which takes two images and combines them in some way. That has two input pads and one output pad. And finally there's a sync node, in this case display, which in this case we show it to the screen. You could also have a node that's wrote a PNG file or added a frame to a video sequence. So this is kind of a mental model of what we're going to construct. We're going to create these 6 nodes and link them together, and they'll display that through the processing. So the first example I'm going to show is how this will be implemented in Ruby. First thing I do is that I require the Gegl library. I create the graph actually, which is a top-level node. In Gegl, graphs themselves can be used as nodes. I'm not doing that in this instance, we'll return to it later in the presentation. So I create new tiles from this graph, which is called graph Gegl. And two of the type load, one Gaussian blur, one of the type opacity, one of the type over, and one of the type display. And those are the operations that the nodes will perform. And there's also some parameters. For the ones on load, I'm setting to PNG files and with the standard deviation, not the radius. This is more mathematically correctly of describing the Gaussian blur. And also set the opacity. And then I'm saying that the output from first load should go into the input of blur, and the output of blur should go into the input of over, and the output of over should go into the input of display. Then I connect the rest of the graph, which is loaded to opacity, into the auxiliary input of over. And finally I'm saying that, okay, display, do your work. That will result in Gegl making sure that all the data that display needs has been processed. I'm not break that up in chunks, but you don't know that using this API. And finally, that buffer is provided to display so it can do its work, and then it comes to sleep for 10 seconds, and let's continue. This is a slightly more verbose example, but it is exactly the same example. I'm just going to talk through this one in detail. This is the C API, or it's rather the human-friendly version of the C API, which is very similar to how G-object in Gegl works, in where you have properties that can be set with values handled in kind of a named key value pairs. The linking is slightly different, but it's exactly the same concepts used. So I'm creating that graph. I'm telling Gegl node process on the display node, sleep for 10 seconds, free up the memory used by the graph, and hit the Gegl library. The entire API of Gegl is contained in a single header file at the moment called Gegl.h. Well, that is kind of possible to duplicate of the definition of the functions from the internal header files. This is the API documentation, which is generated from comments in the header file using kind of the same kind of syntax that people use normally, like GTK doc or Doxigen or Java doc. But I wrote a custom tool just because it's a single header file and I wanted this to be the reference documentation. There is also more language bindings. There is a Python language binding which has the core mapped, but syntactic sugar to make it more convenient to program in Python hasn't been added. But you can construct graphs, read back the values of properties, do processing. And there's yet another way to describe exactly the same thing we had earlier, and that's an XML-based serialization format. Where I load a background image, kind of like background layer, and then there's kind of a effect layer, adjustment layer, filter, whatever you want to call it, which blurs it. And on top of that is another layer, which uses over as its layer mode. And the contents of that layer is another such stack of operations, which starts out with loading the Gegl image, changing the opacity, and that's the result. So this is something that, well, this is currently the serialization format Gegl uses. This is probably not what's going to be the file, next generation file format to begin, but something looking very similar to this. There's also a project called Open Raster, which is kind of cooperation between me as like with these IDs and things based and things before it, and the Krita developers. We're discussing kind of standardizing a way to have an open document-based format with an XML-based description of the hierarchy of layers and how things should be composited together to be able to exchange things between applications. And we do think that we should be able to come up with something that wouldn't be too hard for others to implement and to understand, that will also meet the needs that Gegl can provide for GIMP and the way that including developers have developed the core of Krita. When it comes to how Gegl actually works, I'm not going to talk in detail about all things, but this is a kind of structural overview of the components it consists of. And as you see, there's a blue line going across here, and that's public API. That is the API that is all functionality that is used to implement the Ruby binding, the Python binding, the C# binding, or I'm guessing there will be more language bindings coming up soon. And it's also what GIMP will mostly use. GIMP being kind of a special case customer might actually want to bypass the public API in some instances. But strictly speaking, it shouldn't need to. So there is a public API which is stable. It hasn't actually really changed. You can change your mind. It's like, I don't like the name of that method, so we can rename methods. But I think the only thing we've done since first public release in the end of December, has been renaming methods. We haven't changed what is actually happening. And we're starting to be quite satisfied with how we rename methods. But beyond this public API is the Gegl core. The Gegl core hasn't gotten that much attention as the public API. The Gegl core works. It provides a working implementation doing what the public API kind of proposes that this is what Gegl is supposed to be able to do. But it's going to need to be reworked. Thankfully, that can be done without having to change the public API. The Gegl core builds directly on glib and gobject, which is kind of a nice enhanced standard library for C, giving object orientation, module loading, property setting, and cross-platformness, and takes away a lot of the headaches of working in C. And it's built also on a library called Bubble, which I'll talk a bit more about. The plugin API is in no way stable. It's nice, small, neat, but it will have to change as desires for more capabilities of the engine comes. So I kind of have a very duality kind of based answer to whether people should be hacking plugins for Gegl. I don't want to have to migrate and maintain all the plugins people have written when the API changes, which it will do. But the API as it is now is kind of nice and easy to write plugins for. So I'm not quite sure what will happen there. Perhaps I will write a wish list of these are the plugins that I want and I kind of desire to actually keep moving along if I change the API seriously. And that's also where all kinds of other third-party dependencies come in. It's the plugins depending on them. The Gegl core itself depends on very, very few things. Bubble. Bubble is a universal translator. People familiar with the Hitchhiker's Guide to the Galaxy knows a fish that translates human brain waves, or actually sentient brain waves, into other brain waves in another host, so you can all magically understand other languages. The problem when dealing with graphics often is that there is an awful amount of ways to represent pixels. You have different color models. You have RGB, you have HSV, you have YCVCR, you have LAB, you have HSV, and you have IPVPR. You have a lot. And then you have many, many different data types. You have 32-bit floating point, you have 64-bit floating point, you have 16-bit floating point, you have 8-bit of different variations, you have 16-bit of different variations, and you can probably dream up more other variations of data types. And then you're allowed to mix any color model with any kind of data type, with any permutation of the order of the components. And that's the thing what people do, because when you're writing something, suddenly you just look, I wonder why the heck they're using that kind of pixel format. But all kinds of library I'm interfacing with has this special way of dealing with pixels. So this needs to be handled in a nice way. Okay, those are the implemented color pixel formats in Bubble at the moment. And Bubble is a library where you can actually register. It's like, this is a color model. And this is the way you can transform 64-bit floating point values in RGB with alpha to this other color model. For instance, YUV. So you register one reference conversion to do that job. And you also register, if you need new data types, it's like, this is how I convert a value in the SciIELAB 8-bit integer version for chroma components. That's a special way of encoding pixel data in 8-bit in one of the components in one color model. And you have a reference conversion for that 64-bit floating point as well. Now Bubble knows how to convert 64-bit floating point RGBA into SciIELAB with any of those data types you want to. This might be quite slow, but at least it's able to do it. And on top of that, it has the ability for shortcuts. So the conversions you're actually using quite a bit, for instance, converting 32-bit floating point linear light RGB, which is what Gegl is using internally, to gamma-corrected 8-bit RGB, that can be easily fast. So you can register a shortcut. But Bubble refuses to use that shortcut unless it passes a regression test with random data passed through both the reference implementation, which is kind of slow, and its optimized registered version. So if it passes validation, okay, it will use it. But that's not enough because it's kind of boring about these optimized versions. So Bubble will also allow you to chain together these shortcuts and the regression test them. So this matrix I have here is the current version of Bubble. I'll zoom out. Current version of Bubble with the source format going down the left, and going in columns is destination formats. So the places where there is a single dot is where there is a hand-coded conversion. All the others are where there is a chain of conversions put together, which doesn't lose any quality, but is faster than the reference implementation. And kind of when I'm programming, sometimes, oh, this looks very, very slow. And then I can tell some other program in Gegl to show me where does the time go. And if it says that in one of the nodes, most of the time is spent in Bubble, then, I will run some other introspection, giving me such thing as this, which will highlight which conversions have been used. And if there's a blue dot in one of the blank cells, it tells me here it's using a reference implementation. So I can implement either that one, or one I can see in the neighborhood, and there will be more fast versions available for Bubble to use. One thing that Gegl currently does is that it does processing in chunks. When it's going to render a large image, for instance this presentation, I had it pre-rendered in a cache, but it will kind of start saying, I want to render this small rectangle, and going through the entire large buffer. You probably saw it when I was doing the non-destructive editing, that things were updated in small chunks. The operations in the nodes know what data they need to compute a given rectangle from their inputs. And they also have the ability to say that if this changes in my input, it will affect the following rectangle in my output. And so using that, Gegl is able to determine what's the smallest amount of buffers that needs to be computed to satisfy a given rendering rectangle request. I'm not going to go in details about bits of how that work, but I'm going to show the source code of a plugin. On screen here, I have the entire source code for the brightness contrast operation. It does some kind of nasty C3 processor stuff to hide boilerplate code of GObject away. On the top, it registers that it has two properties, which are doubles, brightness and contrast. Their minimum and maximum values, default values, and documentation string. And then there is the actual name of the operation. It includes the name of this source code file. That's the bizarre thing in this thing. It also says what is the superclass. This is a point filter, which makes it a bit easier for us to write the actual processing function. And there's a description, and it includes the Gegl charms.h file, which charms all the magic incantations that leads to GObject actually working with inheritance and stuff. What it does is that it includes this source file, and those macros are expanded something like 5 times, giving you both the structure containing all the properties, giving you registration of that GObject type system, and adds the code needed to make this be a plugin. So it ends up all this C file, drop another such C file into one of your directories with operations, type make install, and you install a new plugin. The actual processing function for a point filter, a filter that only depends on a single pixel's original value, it could be this new value, takes the actual operation itself as first parameter, pointer to a linear input buffer, linear output buffer, and the count of pixels that it has to process. So there is a loop going through all the pixels, doing arithmetic on the color bits of the pixel, and just setting the alpha of the output to what the input was. By default, Gegl is working in 32-bit RGB floating point with an alpha value. I could here say that, well, this is not what I actually want, and in a more advanced plugin, I would just use bubble to convert things back and forth. The plugins most actually work with just linear buffers. That Gegl internally uses tiles and such things is hidden away. My main motivation for doing that is sanity of programmers, and that code should be readable. If people have tried to study some of the plugins in the game and learn something from them and change code in them, there is a lot of cases and special conditions, and it's optimized quite far away from readability. So I'm going to deny performance optimization to anything in Gegl and say that, well, it probably fixes itself when the architecture changes or something. But it's still quite fast actually, and there's a lot of things that can be optimized with the current architecture. And actually, even having 8-bit and 16-bit versions of all these operations is, in my opinion, nonsense. I would rather have this library be able to make accurate, high-quality results and be usable for signal processing, research, and similar, rather than provide results fast. There's more samples of how one can add operations to Gegl. This is a use of Ruby for generating code. Each of these lines is a plugin. Adding one more line to that array and running the generator will create a new plugin. That's the amount of code I'm comfortable writing to add a new plugin. There might be other ways of doing it, but that is the core of what some of the nodes are actually doing, so it shouldn't be more sophisticated than that. A third way of doing plugins, or adding new functionality, new nodes that can be used, is to create meta operations. That's operations that are built up from core components, other operations or nodes that exist. And the example here is a drop shadow. The graph shown here is output done layouted with graph this and just introspection of Gegl was it running. So kind of the order is how I would lay them out manually. We have loading of the background image, and we have loading of the Gegl logo, which is shifted, translated, and about a drop shadow too, and then composited over the background image before it's passed down to some kind of output. Drop shadow itself is a graph, which is the graph in the middle there. And the input image is loaded, and using ported up compositing operators, there's a duplicate version of it, which is made black, which is blurred, and over that duplicated version is the original, and the result of this compositing is the output that's handed out. So this graph is the drop shadow operation of Gegl, and it's kind of written in Gegl itself. And the way of doing that isn't like I would like it to be at the moment. You have to write C code to hook up that graph, and you have no real way of setting properties. I imagine that the way to do this would be an XML file or something, and not having to write code. How is my time?
I still have 15 minutes.
Okay. Future work. There's a lot of things I can talk about there. But feel free to break in and start asking me questions. For the core of Gegl, one of the main new things that I want to add there is parallel and perhaps distributed processing. At the moment, this machine is a dual core machine, but only one of the cores are active, because Gegl is single process at the moment. I kind of actually suspect that once I start doing that and try to make it multi-threaded, it won't be much of an issue because the operations themselves are already re-entered for other purposes. But I consciously avoided starting hacking that for FOSDEM because I fear that if I did, it was definitely going to be more work than I suspected, and I wouldn't have time to prepare a presentation. More sophisticated caching. As it is now, Gegl is only caching the output. What in GIMP is called the projection is the final random image of all the layers. It is possible to cache things on more levels, to add a cache on every node in the graph. And by doing so, Gegl wouldn't have to recompute everything from the loaded files all the way up to the displayed image. When you were dragging a layer around, stop. Up to this point in the graph, already have the results. So when this thing is dragged over it, I only need to compute things from there and forward. And that would make it very much faster already for an interactive application like this one. It would be nice to replace the entire way of writing operations and processing with something that used the just-in-time compiler. That would be retardable, and perhaps that would be a way to have GPU acceleration. That's more similar to the original plans for Gegl. Suppose use something called Gegl, the general image language, which was kind of a preprocessor for generating 8-bit, 16-bit, 2-bit versions of all operations. I don't think that's the reason I actually wanted just-in-time compiler. It will be more for this reason, to be able to use hardware-aided acceleration architectures. Bubble itself, which is a foundation of Gegl, has a problem in that it uses RGBA as its kind of intermediate conversion format. And for most applications, that's not a problem. Most color models people work with are three-dimensional, or three-stimulus color models. And there's one exception, and that's CMYK, which has 4 components. And if you have CMYK with alpha, okay, you have alpha components, kind of a 5-dimensional space. And the problem is that you will have information loss going from CMYK-A to RGBA and to another high-dimensional format. I'm not quite sure if this belongs in Bubble or not, I haven't decided. But ideally I would want Bubble to be able to deal with spectral data. It's kind of aiming rather high, but it's fun to work with spectral images. But I think most of that actually belongs outside. Different libraries doing color management like little CMS, and rather just keep using the sRGB primaries internally in Gegl and Bubble. Yes?
Have you looked at GLSL as a unique pixel processing language?
I haven't really looked into it. At the moment, I kind of just, for the operations and what's within Gegl, that's just there as kind of a side effect of stabilizing the public API.
We have x86, we have.
Yeah, you're talking about Polar and Jolt and such, or?
No, actually in Mesa.
Oh.
GLSL. Parallel processing language.
Well, it might be interesting to write a kind of small Gegl backend that only does that kind of processing. Because if you have a small core set of the operations that at the moment are in C, you wouldn't have to change public API. So if you could create a different thing that would be faster, it would be nice for previews and such. There's one thing I didn't add to this list, which is rather important. and that's the ability to scale parameters so that when you request pseudo version like this, I wouldn't have to actually do all the rendering. Okay, I wasn't finished with that non-destructive and didn't care about this and wasn't visible. But that it could work on scaled down versions of all the images to create this result. And to be able to do that, all the operations, all the plugins, need to be able to understand what it means that you have a scale factor included in how the processing is done. That's okay for all point operations like in FOSDEM, that's no problem. For a Gaussian blur, it's no problem. For scaling, rotation, or other fine operations, it's not a problem. And by doing that, you also have things like unsharp masking, which is actually just a meta operation on top of Gaussian blur. You start having almost all the things you actually kind of need for basic photo editing. You should be able to have live previews that are lightning fast without big issue. It's not there yet, so when Gegl now works, it will have to process the full resolution image to get that data. But that should be possible to actually change without changing the public API. There's other abstractions on top of Gegl that would be fun to have. And that's the ability to actually do animations, animated properties, etc. But that doesn't belong in the core section, that belongs somewhere else. This application, by the way, which I'm using for this presentation, is written in Ruby, and I'll probably blog about it and put the source online when I have network and time to do it. It's kind of neat, but mostly hacked together to actually just demonstrate Gegl. There's a set of operations that also would be nice to have. It's like lib open roll to read the grayscale data directly from raw photo files. At the moment, I'm using that through DC raw, but I don't like having to just ask for a large chunk of data, waiting for another process to give me that grayscale image in one big chunk. I want more direct access to it. And more advanced, they are demosaicing routines. At the moment, with low raw data, it sucks more than most things you could probably see because it does some layers neighbor stuff. Noise reduction. There is some noise reduction already implemented, but porting more wouldn't really hurt. Tone mapping, the ability to do frequency domain processing in the Fourier domain. It's quite close to have a full SVG 1.1 filter set implemented, so being able to claim that it conforms to that would be nice. So those are on my wish list. Gegl at the moment isn't able to implement painting with brushes, like one of the core things of GIMP to do, or rather, it's able, but it doesn't have the plugins needed to do exactly that. I did a prototype test of doing that, and it works nice. I'll talk about animated properties. I did have a project earlier, which kind of went under the radar for most people, which was video editor compositing application, which was built on the predecessor to Gegl called Gegl, or rather one predecessor to Gegl. It was a separate project that I coded. I used it for creating a few music videos. That application probably is impossible to build right now, and the reason for that is that it was written at a time before the Cairo API was stable. So it had a rather expensive set of custom Cairo widgets and a mixture of GTK and Cairo before GTK included Cairo. But most of those things should be easily to re-implement on top of Gegl now. Just this week, I started hacking together the FFmpeg input and output operations. So one sample of using that is, okay, this is not the way that Elephant Stream actually looks. This is more a tunified version. And the reason I actually coded up the FOSDEM input and output operations was that I wanted to test, just figure out what actually on live video. So within the Gegl source code, there is a directory called operations, and within there is a directory called workshop, and those are all the plugins that are not compiled by default. My workshop contains quite a bit more things than the one in Subversion, but there is also the ffload and ffsave. What I wanted to show was just a small Ruby script called test, which is the thing that generated. I think I actually will load up. That is the Ruby script I used to generate the video file that was kind of a cartoon-like version of Elephant 3, requiring Gegl and setting up a small graph where I'm using a that's actually a filter that's not in Subversion yet, but will be checked in soon, which is edge-enhancing blur filter, edge-preserving and edge-enhancing blur filter, which ends up actually being cartoonification and running multiple iterations. So I have a source node loading with FOSDEM, 3 such filters, and FOSDEM save at the end, connect together with graph, which is actually just a chain. And within Ruby is saying that 240 times do such a thing that you set the property frame on the source node to be a frame number decided. And tell it to process once. Then you process the graph and append the frame to the video. And each time it does that, it adds a frame to the output video, and when it's done, there is a video file. Then I'm talking for 40 minutes. And want more questions? Yes?
Is double level API stable or usable in external?
The bubble API is very, very small. The essence of, I can show the bubble documentation. The basic usage of bubble is saying that you want bubble to process. You want to run a Babel process on a Babel fish. You create a Babel fish by saying what is the source format and output format. You can use all the names that are listed in the reference of Babel. And a pointer to the input and output buffer and how large those buffers are. That is at least kind of the core of the API. You can also construct new formats. That's kind of, if you start doing that, you're more on unstable ground, but don't see that changing very much either. It's like you say that the model here is corrected RGB. The following components now will be of type unsigned date. And in this case, it's actually, instead of RGB, it's VTR, opposite order in memory of the bytes. And many have constructed new formats which could be used in place of those strings in creating the bubble fish. And when it comes to the list of implemented things, those are the data types in bubble. And that is the color models. I have separate color models for gamma corrected and non-gamma corrected, as well as pre-multiplied alpha and not pre-multiplied alpha. The reason for that is that I had a core that worked, and just treating them as separate color models, I didn't have to add any more things to it. I see no reason to actually change it since it works. That's kind of, from a very kind of structured point of view, we would actually have a special property like the pre-multiplied alpha, non-pre-multiplied alpha. But as long as I keep the core set of color models low, this will still work. And that's the same as you saw earlier with the supported color formats. This list is generated through introspection. I would say that the API to query what are the available pixel formats and how they're composed of components and things is probably something that will change more than the kind of basic usage of it. But if you only have like you have data in this format and another format, you need to convert between them. There's a very, very small API that needs to be used, and that will probably not change. Other questions? Yes?
I saw the video for Linux support. Is there an API to detect what are the webcam of the computer and things like that? What does that mean for Linux computer?
Well, it was listed as kind of a dependency of operations. For me, that means you have a node which you can set the device on, use this device, and configure the width and height of the image buffer you get from there, and you can pick up into the processing graph. And the implementation of that is a little bit unstable. It's much easier with the video format where you say, use this video file and give me a frame of 150, because that doesn't change. A video for Linux device actually changes over time continuously. So the kind of dirt handling or damage handling of the composited image isn't quite as nice with Beautiful Linux as a video file. So I haven't quite decided how to do that in a clean way. What? Yeah, but that it doesn't have anything to do with those issues. It's the issue of the thing that continuously changes in time. I want to be able to cache results. It's like, this is fine. Unless parameters change, I don't have to redo this work. But with a live video source, you actually have to continuously do processing. And that's not really the kind of thing that the Gegl is designed to do. I do want to do it still, so I'll try to find a way to make it work nicely for us.
How far off is this moving again? So you say, okay, this is far enough, and now the operating game, when the game develops it now, we're good.
Well, I'm kind of a game developer, but I'm kind of remaining on the side of the fence of Gegl. So the game developers will probably be my customers in the kind of that respect. I think that Gegl has a public API that shouldn't need to change much for Gegl to use it. They are still claiming that they will access the internal header files and directly manipulate the objects. Okay, probably don't need to do that. That's my opinion on it. I think it actually it's not probably not fast enough, but some of these things will change, and it's already in a state where integration can start. So it's no longer GIMP that's waiting for Gegl, it's Gegl that's waiting for GIMP. I think there was another question up there? No?
Just a small question about operations. What's the data type that are you using for coding things like the internal data that is used?
The internal data type is?
Yes, you just showed the brightness and contrast
Yes.
Is that are you doing always source or will the vertical there?
The operations themselves, the point operations are all done in floating point, like brightness, contrast, and threshold. But if you're coding an operation from scratch, you would have a Gegl buffer. And from a Gegl buffer, you can request data into a linear buffer that you're going to work on. And when you're requesting that linear buffer, you're using bubble. So you can say that I want to have 64-bit LAB in a linear buffer. And then you can change your data or compute a new linear buffer. And then you write that linear buffer saying, write this to the Gegl buffer as the output, and this is the format of linear buffer I'm providing. So you're working on linear buffer in whichever data representation you actually want to have yourself. But if you're always working on distributed floating point, and bubble matching doesn't have to really work, because it's probably got distributed floating point data already. So almost all the operations at the moment are distributed floating point RGBA, which leads to the least amount of conversions, and it's high enough quality for the things I want to do. Yes?
What file formats do you presently support high dynamic resolution? Or do you, normal JPEG files or GIF files or PNG files are regular RGB data, but you aim to have high dynamic resolution. That's right. What kind of file formats do you use to store that data?
At the moment, the focus on file format has been mostly on input. So there is file loaders for PNG, JPEG, and OpenEXR. OpenEXR being the only one that's high dynamic range. It supports loading 16-bit PNG files. When it comes to saving things, there hasn't been much focus on saving things in Gegl. It supports saving PNG. I think it supports both 16-bit and 8-bit PNGs, I'm not sure. And it supports, as of the day before yesterday, saving any video format that Olympic supports. I haven't started playing with creating animations yet, but it should be rather simple to create some interesting things for video. So my answer there is, well, at the moment, not that many, but adding source operations and sync operations isn't that much work either. And I think someone is working on clip support, for loading at least. When it comes to saving, I don't know. I'm more focused on getting the results to the screen than to the disk.
So, are you interested in making your own file format?
Not for, well, I already actually have kind of file format because the stack files can be loaded back in. But when it comes, for instance, to Open Raster, this initiative together with Krita, and that would be a file format for an entire structured layered image. And within that, we are, at the moment at least, aiming to reuse JPEG, perhaps for low quality versions, but PNG, since it has both 8-bit, 16-bit, alpha, RGB, and grayscale, and perhaps reuse OpenEXR in addition for high dynamic range layers. And that would be it in a container that has an XML catalog describing it, the structure, how things are connected together, and all of this probably within a zip file, similar to other open document formats.
Last question.
Yeah, question about dynamic range images. Do you have operation or special or anything to generate dynamic range images from on that JPEG
No. Until I myself decide. I know what you mean. You're asking whether there is a way to create a high dynamic range image from bracketed shots, so that you have on a single location you shoot 4 or 5 frames in different exposures. And okay, both that operation to create the high dynamic range image from low dynamic range images, as well as proper tone mapping are both things that's missing, but can easily be added within the architecture.